Here we are. Okay, we're recording. So, yesterday we were talking about the first derivative test. Then we got to the point of discussing this idea of concavity. Let's get back to this idea of concavity. If you have a function that goes like this, then the concavity points down. This is called concave down. What I discussed yesterday is how in this sort of scenario, the derivative is decreasing. You see the slopes of tangent lines are decreasing in this image. And so the second derivative is negative. And if you flip that curve upside down and say curving up, the concavity points upwards. We call this concave up. In this image, the derivative would be increasing. And so the second derivative is positive. Okay, it's possible to have a curve that does something like this, for example. And in an image like this, you might have concave down, and then it switches to concave up. And at that point where the switch occurs, that point is called an inflection point. This occurs where the second derivative changes sign. Okay. Occurs where the second derivative changes sign. So today we're going to do an analysis of a function. I neglected to really prepare one, so I'm going to nab Desmos here and just grab a good one. It's going to make a good one real quick. Just take me a second. Perfect. Okay. I'm ready. All right. So let's take, for example, f of x is x cubed minus 4x squared plus 4x plus 1. Okay. It's a cubic polynomial. Okay. Well, first, we're going to go through a few steps. We're going to find critical numbers. Actually, no. Let's skip. We'll do that maybe second. the first thing I want to do is we're going to analyze concavity. To do this, we'll find the second derivative, find where the second derivative equals 0 or is undefined, and then we'll do a sign chart. A sign chart or a sign analysis for the second derivative. And then from that, we'll find intervals of concavity and inflection points. Okay, so first step, find the derivative. I differentiate my my nice function here, my cubic function. You just use the power rule, nice and easy. 8x plus 4 plus 0. So there's my first derivative. Then I'll do a second derivative. 6x minus 8. Good. 6x minus 8. So what I want to do is figure out where does the second derivative change sign? Right? Where could it possibly change sign? Not necessarily, but where could it possibly change sign? This is very similar to finding critical numbers, but they're not critical numbers because they're not for the first derivative, for the second derivative. So this right here, where the second derivative equals 0 or undefined, not critical numbers, but they don't have a name. So I actually met a guy, a fellow teacher named Roger Hergert, who had sort of jokingly named these numbers after himself. So we call them Hergert numbers, he and I. So the Hergert numbers are they're like the equivalent of critical numbers, but for the second derivative, where the second derivative is equal to 0 or it's undefined. So we'll find those Hergert numbers now. All right, well, second derivative equals 0 when this function is 0. So if 6x minus 8 is 0, then like 6x has to equal 8, right? You have to add the 8 to both sides. Divide by 6, and x is 8 over 6, or 4/3, or 1.3 repeated. Okay, 4/3. So that is our x value where f double prime equals 0. Is f double prime ever undefined? It's a polynomial. It's 6x minus 8. Polynomials are never undefined. But I have to state that. Okay, I have to check both of these boxes here. Check that and check that, just to make sure that here, let's make them boxes. Gonna make sure I check both of those to make sure that I found all of those numbers. Okay, so now there's one number, this number right here. And so now with that number, I can make a sign chart for the second derivative. The sign chart goes like this. You plot those Hergert numbers. I'm just going to plot a number at 4/3, so 1.3 repeated. Okay. And those numbers then break the entire domain, which is for this function is all real numbers. They break the domain up into intervals. So we have two intervals here. We have the interval on the left. We have the interval on the right. So I'm going to pick a number here and pick a number here. So I'm picking test numbers in my intervals. And these intervals go all the way to infinity, right? All the way off that way, all the way off that way. So for test numbers, I'm going to pick 1 and 2. They just need to be numbers to the left and right of 1 1/3. So what I'm going to do with those test numbers is I'm going to put them right back into the function that we're doing the sign chart for, right? Which is the second derivative. We want to determine whether the second derivative is positive or negative so that we can determine concavity. So all I need to do is plug this one back into here. So I have 6 minus 8. This is -2. So that's a negative number. So it's negative on that entire interval. And then if I plug in 2, I get 12 minus 8, which is what? 4. So that's a positive number. So it's positive on that interval and the entire interval. Okay. There we go. So there's our little sign chart. And so now we can make our conclusion from this information. We can say that f, the original function we're analyzing, is concave up on the interval from 1.3 repeated all the way out to infinity, because that's where we have a positive second derivative. It is concave down on the interval from negative infinity up to 1.3 repeated. That's the interval on the left. Oops. And it has an inflection point at that x equals 1 1/3, because we see a genuine change in concavity. The sign of the second derivative changes from negative to positive at that point. So that is our concavity analysis, our sign analysis of the second derivative, which tells us all this information about which direction the function is curving. Okay, so now if I show you what this function looks like in Desmos, you will see everything we just discovered reflected in this graph. So here is the function. This is what it looks like. Okay, and if we plot the point 1.3 repeated, and then f of 1.3 repeated, okay, that point is right there. That is our inflection point. Right there. Okay. That is the point on the graph where the concavity changes from down to up. Okay. All right, everybody, just a second.
Okay, folks. So because I don't want to put my child on YouTube, I'm gonna end the recording for today. So please take good notes for the rest of the class.